Hello students, welcome back to the series Coordination Chemistry. This is the 7th module of the series Theories of Coordination Compounds. Here we discuss different theories of coordination compounds. We have already discussed in the previous classes about the preliminary theories, that is Werner's coordination theory, Sidgwick's concept and the valence bond theory. In this class, we will be discussing the most important theory, that is a modern theory, crystal field theory. So, crystal field theory was first proposed by Hans Bethe in 1929 and it was extended by Van Vleck in 1935. So, these two scientists altogether they proposed the crystal field theory. And it describes the breaking of orbital degeneracy in transition metal complexes due to the presence of ligands. And this theory is all about the breaking of the degeneracy of the d orbitals by the presence of the ligands. And now we have several postulates for crystal field theory. Number one is the central metal ion and the ligands are considered as the point charges. That is the most important thing in this theory. The central metal atom and ligands are considered as point charges. And the interaction between the central metal atom or ion and ligands, it is purely electrostatic in nature. That is, the interaction is between metal ion and negative ion or negative end of the ligand dipole. So, the interaction between the central metal atom and ligand is purely electrostatic because the central metal atom and ligands are considered as a point charges. There is an interaction between the metal and ligand, that is a positive central metal atom and negative end of the ligand, and thus the formation of a metal ligand bond is formed. And now all the d orbitals of the central metal ion have the same energy or they are degenerate. We know that in the case of d orbitals, there are 5 d orbitals and all the 5 d orbitals are degenerate. Degenerate means they are having same energy. And the electrons of the positive ion and that of the ligands tend to repel each other. They undergo repulsive interaction. Again, the electrons of the positive ion, that is positive ion is central metal atom, and that of the ligands, they tend to repel each other. They undergo repulsive interaction because positive ion central metal atom is also having electrons and the ligands are also having electrons. When electron comes together, there will be a repulsive interaction. By the approach of the ligands, the degeneracy is lost due to the electron-electron repulsion. So, in the crystal field theory, it is all about the removal of degeneracy of the d orbital. Why the degeneracy of the d orbital is removed? Because the electron-electron repulsion. How electron-electron repulsion happens? The metal ion is having electrons and ligands are also having electrons. When ligands approach the metal orbitals, the d orbitals which were degenerate in metal ion or metal atom, they will be removed. That degeneracy will be removed or they will split up into different energy levels. That degeneracy will be removed and will be splitted into 2 types. See the shapes of d orbitals. You may be familiar with the shape of d orbitals in your lower classes. You can see that we have 5 d orbitals. 5 d orbitals are there. All the d orbitals are degenerate. And d orbitals are named as, first it is dxy, dxz, dyz, dx square minus y square and dz square. So, thus we have 5 d orbitals with different orientation. See, these 3 are having their lobes in between the axis. This is the axis, x and y axis. So, dxy means it is having its d electron lobe, d orbital lobe is in between x and y axis, that is why it is dxy. And the dxz means its lobes are between x and z axis. dyz means the lobes are between y and z axis. Okay. And but these two d orbitals, they are having their lobes along the axis. Since it is named as dx square minus y square, the lobes are along x axis and y axis, along the axis, but these three are having their lobes in between their axis. And in the case of dz square, you can see their lobe, its lobe is along the z axis and an annulus in the y axis. This is the orientation of d orbitals, 5 d orbitals. All the 5 d orbitals are degenerate in the absence of ligands. When ligands are absent, all the orbitals are same or they are degenerate. By the approach of these ligands, this degeneracy is lost and they will split up into different energy levels. Okay. And now, the splitting depends on the orientation of the d orbitals. See, we have already shown the figure. In the figure, you have seen that the d orbital orientation is different in all the cases, and that splitting, when the ligands come, the d orbitals will be splitted, and the splitting will be depending upon the orientation of these d orbitals. Among the d orbitals, 3 of the d orbitals, that is dxy, dxz, dyz, these 3 d orbitals lies in between the axis and they are grouped as T2G. See, T2G. They are grouped together as T2G set. And the other two, that is dx square minus y square and dz square, they are lying along the axis. That is, in case of dx square minus y square, it is lying along x axis and y axis. In the case of z square, it is along the z axis. So, these two are lying along the axis, and they are both these are grouped as EG. It is EG, T2G and EG. And you might be, you might be wondering, what is G, what is G, E and G. This T2G and EG, why this G is included in this case? We are speaking about the octahedral complexes. In octahedral complexes, you have a symmetry. Octahedral complexes are symmetric, and that is why you can use gerade. G means gerade. G is gerade. U means ungerade. Gerade and ungerade. Gerade means symmetric, ungerade means it is not having any symmetry. So, EG and T2G. When we are discussing about octahedral complexes, splitting in octahedral complexes, we will be using the term G there, T2G and EG. But in the case of tetrahedral complexes, there are no symmetry, then G will be removed. It will be simply notated as or denoted as T2 and E. No G will be used. And again, how the d orbitals are being splitted. The free metal ion has 5 d orbitals. They are all degenerate in the absence of ligands. And consider a hypothetical situation where the metal atom is surrounded spherically by the negative ligands. Suppose you have had to consider central metal atom is at the center, and around this central metal atom there is a spherical surrounding. Spherically it is surrounded by the ligands, negatively charged ligands. And so, there will be the energy of the d orbitals. In such a situation, the energy of d orbitals will increase. Why? Because this ligands are having, negatively charged ligands are coming. When they are approaching the central metal atom, the energy of that atom will increase because of the electron-electron repulsion. But this increase in energy will be to the same extent because it is spherical surrounding of the negative charges. It is a hypothetical situation. And further approach of the ligands will cause the splitting in the orbitals. If the ligands are approaching further, it will be in a particular fashion, and according to the approach of the ligands, the d orbitals will split. It will be discussed very clearly in the coming slides. The energy of d orbitals lying along the ligand, the energy of the ligand orbitals, d orbitals lying along the ligand charge, that rises than that lying in between the point charges of the ligand. See, I can draw this is the octahedral complex, and in octahedral complex you have the ligands, 6 ligands, 1, 2, 3, 4, 5 and 6 ligands are there. And you know this central metal atom is there, central metal atom is having its d orbitals, 5 d orbitals are there, 5 different d orbitals, 3 of them are having their lobes in between the axis, 2 of them are having the lobes along the axis. And if the ligands are coming along the axis, if the ligands approach the central metal atom along the axis, the d orbitals which are having their lobes along the axis will be experiencing a higher repulsion when compared to the d orbitals having their lobes in between the axis. So, in octahedral complexes, the splitting will be into 2, and that splitting will be depending on how the ligands are approaching. If they are in the octahedral complex, the ligands are approaching along the axis, that is why the d orbitals lying along the axis will be experiencing a greater repulsion and their energy will be rising, and 3 of them are having their d orbitals in between the axis, they will be having a lower energy, and the splitting pattern will be discussed. And the splitting of d orbitals in octahedral complexes, again you can understand in each step. For example, consider a molecule with octahedral geometry. We are considering a molecule, the ligands are approaching the metal ion along the axis. Along the axis, that is why it is XX, YY, ZZ, means along x axis, along y axis and along z axis. Okay. And now this is the situation. We know that our central metal atom, we have 5 d orbitals, all of them are degenerate, 5 having the same energy. Now, this is a hypothetical situation, that is the ligands are spherically surrounded, this metal atom is surrounded by the spherically surrounded by the ligands. So, there is a uniform distribution or uniform surrounding of the ligands, and when this type of approaching or this type of arrangement is there, the increase of energy happens because of the electron repulsion. So, this is the energy along, energy is increasing. So, from here energy rises, but the degeneracy is still maintained here because there is a spherical arrangement of ligands. This is a hypothetical situation. And now, in the case of octahedral complexes, the ligands are actually approaching along the axis, and now when ligands are coming closer to the central metal atom, they will be along the axis. Along the axis means the metal d orbitals which are having their lobes along the axis experiences a higher repulsion, and they will be rising the energy. That is why it will be splitting. This will be splitting like this. Dx square minus y square and dz square, these are having their lobes along the axis, they are having a higher energy, but these 3 are having lower energy because their lobes are having, they are having their lobes in between the axis. So, they will be experiencing less energy, less repulsion. See this is the splitting of d orbitals, that is dxy, dxz, dyz orbital will be splitted, they will be having the lower energy, and these 2 will be having the higher energy. And the splitting means this degenerate orbitals are splitted into 2, and the energy difference between these 2 are termed as delta O, crystal field splitting, that is called as crystal field splitting, delta O. Okay. And now, the energies of the dz square and dx square minus y square orbitals increases due to the greater interaction of the ligands, and that set is called EG set, that I have already told, that is dz square and dx square minus y square are totally, they are combined as the EG set. Dx, xy, dxz, dyz orbitals, they will have a decrease in energy with respect to its normal energy level, and they are becoming more stable, that is the 3 of them are grouped as T2G set. and the energy difference between T2G and EG orbitals, it is called as delta O. It is called the crystal field splitting, or delta O can be, delta O is equal to 10 dq. dq means differential of quanta. dq means differential of quanta. So, delta O is the difference in energy between T2G set and EG set. Now, splitting does not alter the average energy of the d orbitals. See, the d orbitals are, some are having a greater energy, some are having less energy, right. So, it does not actually alter the average energy of the d orbitals remains same. And due to the crystal field splitting, EG orbitals are raised by an amount of energy 0.6 delta O. That is, EG orbitals means two of them were EG orbitals, d x square minus y square, d z square. They will be raised by an amount of energy 0.6 delta O. But these T2G orbitals, 3 T2G orbitals will be having a lower energy, or they are stabilized by an amount of minus 0.6 delta O. Why minus is included? Because to show stabilization, minus 0.4 delta O. In the upper side you can see 0.6 delta O, it is plus 0.6 delta O. And now here you can calculate the crystal field stabilization energy in different systems. For example, if I take a D1 system means a coordination complex which is having D1 electron, that is one electron in the d orbital. Okay. So, the central metal atom which is having one electron in d orbital, it is called the D1 system. Now, D1 system means you know that you have 5 d orbitals, all of them are degenerate when in the absence of ligand, that is shown here. See this, one electron in the d orbital, these are the d 1, 2, 3, 4, 5 d orbitals, all are degenerate. By the approach of ligands, this will be splitted into two. They will be splitted into EG and T2G. EG means there are two orbitals, 3 orbitals in the T2G set. Okay. And now, while filling, once it is split, that is once ligands are approaching, that will be splitted into two, into T2G and EG. Now, electrons will be filling according to our basic principles, that is Hund's rule of maximum multiplicity, Aufbau principle, etc. And you know, the lowest energy will be filled first, which is having lowest energy, T2G or EG. T2G set is having lowest energy. So, this electron will be going to here or here or here. You can write, for simplicity I am writing it here, because all the three, these three are degenerate, all the three are having same energy. Now, you have the stabilization energy of minus 0.4 delta O. This is stabilized by this amount, minus 0.4 delta O. This is destabilized by 0.6 delta O. Okay. And now, how to calculate the crystal field stabilization energy? You can calculate it by giving the number of electrons. How many electrons are there in the T2G set? 1 electron. So, 1 into, and what is the stabilization energy of the T2G set? It is minus 4 delta O. So, 1 into minus 4 delta O, we get minus 4 delta O. And I have already taught that delta O equal to 10 dq. Delta O equal to 10 dq means I will give minus 4 dq, minus 4 dq, it is minus 4 dq. In terms of dq, you can write it as minus 4 dq. In terms of delta O, you can write as minus 0.4 delta O. Okay. So, that is all about the D1 system. And now, moving to the D2 system. D2 means 2 electrons in the d orbitals, a system which is having, or a central metal atom which is having 2 electrons in the d orbital. Now, the d orbitals are degenerate, 5 d orbitals in the absence of ligands. When ligands are coming, it will be splitted into two, T2G and EG. Now, electrons will be filled according to the Aufbau principle, that is lowest energy lowest energy to the highest energy, that should be followed. So, lowest energy is this 1, 2 2 electrons should be filled, and you should follow the Hund's rule of maximum multiplicity also, because all should be singly filled and then pairing occurs. So, all should be singly filled, after that only you can pair. That is what happening here. And now you can calculate the crystal field stabilization energy. While calculating, how many electrons are there in T2G set? 2 electrons. So, 2 into what is the stabilization energy of the T2G set? It is minus 0.4 delta O. So, 2 into minus 0.4 delta O, that is minus 0.8 delta O, or you can write it at it is minus, this is minus 8 dq. Okay. It is minus 8 in terms of dq, it is minus 8 dq. In terms of delta O, it is minus 0.8 delta O. And next, this is the case of the D3 system also, the same case, you have to just multiply it with 3. And now moving to the D4 system. In the case of D4 system, the case is somewhat different. In the system, the electronic arrangement depends upon delta O, that is the splitting, crystal field splitting, and the pairing energy. If delta O is less than the pairing energy, then if delta O is less than the pairing energy, the electron will be moving upper side, that is in the EG orbital, it will move to the EG orbital. You can discuss in the coming slides. For the D4 system, in the system the electronic, in the D4 system, you have 2 different cases, that is case 1 and case 2. You have different possibilities. I will be explaining, that is D4 means 4 electron in the D orbital, all the degenerate D orbitals are there. In the absence of ligand, electrons will be like this. When ligands approaches, they will be splitted. Now, how to fill the electrons? You have to fill the electrons 1, 2, 3. And the 4th electron, it can go there, it can go to the EG orbital, or it can be paired here. There are 2 possibilities here while filling 1, 2, 3, and the 4th electron can go, either it can go there or the 4th one can be paired here. It will be depending upon the value of delta O value and the pairing energy value. Pairing energy means the energy that should be overcome to pair an electron. I will be explaining it in detail. And while calculating, this is a case 1. In the case 1, if the delta O value is less, this is the case where delta O value is less. Delta O is less means what? The splitting is less, which means that this electron, the 4th electron, can easily go there, because the splitting is less. Since splitting is less, it will be very easy for the 4th one to go there. So, this is that case 1 where delta O is less. In that case, crystal field stabilization energy can be calculated by multiplying how many electrons in the T2G set? 3. And what is the stabilization energy of this set? It is minus 0.4 delta O. So, 3 into minus 0.4 delta O, plus we have to 1 electron is there in the EG set, plus 1 into what is the destabilization energy of the EG set? It is 0.6 delta O. So, plus 1 into 0.6 delta O, that is 1.2, and you get 1.2 and 6, that is minus 0.6 delta O, minus 0.6 delta O. This is the crystal field stabilization energy, minus 0.6 delta O, or in terms of dq you can write as minus 6 dq. And in this case, it is a high spin complex. When it is a high spin complex, this type of arrangement happens. Why it is a high spin complex? Because spins are maximum. This is the spins, number of unpaired electrons, right? So, the 4th one has a possibility to pair here. The spin, as there is a possibility to get a spin paired structure, but instead of spin pairing, electron is going upper side. That is why it is having a high spin structure, high spin complex. And now the case 2, that is the D4 system, again D4 system, case 2, the other possibility is to pair here, right? in this case this will be having a delta O is high, delta O is high, which means that the splitting is very high. The splitting between the T2G and EG is very high. Since splitting is greater, it will be very difficult for this the fourth electron to go there. Instead, it will be paired, or you can say that pairing energy is less than, pairing energy means I can write it as P, pairing energy is less than delta O, or it is easier to pair an electron. So, pairing energy is less than delta O in this case. And while calculating the crystal field stabilization energy, you can number the electrons. How many electrons? 1, 2, 3, 4. 4 into stabilization energy minus 0.4 delta O plus pairing energy. Pairing energy means what? The energy that is needed to pair this fourth electron, that should be added here. Again I repeat, while calculating the crystal field stabilization energy, we have to number the electrons. How many electrons are there in T2G set? 4 electrons. So, 4 into minus 0.4 delta O plus we have to include the pairing energy. Why? Pairing energy means it is the energy needed to pair the fourth one, otherwise it could go there, right. So, instead of going there, we are pairing this fourth one. So, we have to overcome that energy also, that should be added here. And now, what is the final result? It is minus 1.6 delta O plus pairing energy. You have to write that also, minus 1.6 delta O plus pairing energy. This is the crystal field stabilization energy in the case of D4 low spin complex. Why it is called as low spin? It has a possibility to go there, that is to get a higher spin, there is a possibility, but instead that it is been paired and the spin has been reduced, that is why it is called as a low spin complex. And now you have to go for another D5 system. D5 means 5 electrons in the d orbitals. Again here also you can have two cases, that is low spin and high spin cases, because 5 electrons are there in the d orbital, and case 1 is we are actually having all the electrons in the T2G orbital, that is in this case delta O is greater than this pairing energy. Pairing energy is less when compared to delta O, which means that higher splitting is there. So, the 1, 2, 3 and 4th and 5th electron is not going upside, it is simply paired here only. And now while calculating the crystal field stabilization energy, you can count the number of electrons in the T2G set, that is 5 into minus 0.4 delta O plus 2 pairing energy, because 2 of them are being paired here instead of going in the upper state, they are being paired, and this much energy has to be overcome, or we have to add this much energy along with the crystal field stabilization energy, and you get the value as minus 2 delta O plus 2 pairing energy, or the complex is a low spin complex, right, and this is the case 1. And now moving to the second possibility, in the same situation D5 complex, there is another possibility that the 3 electrons in the T2 and the 4th and 5th will be going to the EG set. This is the case where delta O is less than, it is less than the pairing energy, or you can say that pairing energy is more than the crystal field splitting. So, the 3rd and 4th will be excited or will be moved to the upper state. And now while calculating the crystal field stabilization energy, you have to add the number of electrons in T2G set, that is 3 into the stabilization energy of T2G, that is minus 0.4 delta O plus number of electrons in the EG set, that is 2 into plus 0.6 delta O. On the whole, if we add, you will get 0 delta O, that is crystal field stabilization energy is 0 in the case of high spin D5 complex. Okay. And now moving to the next system, D6 system. D6 means 6 electrons in the d orbitals. Again 6 electrons are being arranged in the degenerate d orbitals. By the approach of ligands, they are being splitted in this into 2. Here also 2 possibilities will be there, either the electrons can be paired or it can be moved to the higher level. In the first case, this is the case where we are pairing the electrons, and while filling the electrons, first electron is added here, 1, 2, 3, we are adding 3, and the fourth is being again paired here, fifth again paired here, sixth is also paired here. And now while calculating the CFSE, how many electrons in T2G? 6 electrons, 6 into the stabilization energy, that is minus 0.4 delta O. And now what is the pairing energy here? You may be thinking that the pairing energy is 3 pairing energy, but actually it is not the case. 3 is not the, you have only 2 pairing energy. Why? Because the possibility is like this. This is the case, right? This is the case. If we are filling 1, 2, this is the D6 system, 1, 2, 3, 1, 2, 3. If it is a high spin complex, you can actually fill like this, 1, 2, 3, 4, 5, and 6 will be again coming here because it is having a lower energy, right? 1, 2, 3, 4, 5, and the sixth one will be here. If in the second case, if this is the first case, in the second case the arrangement will be like this, and in that arrangement itself there is a pairing in the first case. So, first d orbital or first T2G set, first orbital in the T2G orbital. So, already a paired structure is there, and now we are forcefully pairing only this 2 in this case. In this case we are actually, this is paired in the second case, you can see in the second case. This is the case 2. Case 2 means a high spin complex. Here this is paired, already paired, but in this case we are actually pairing extra, additionally we are pairing these 2 only. So, we have to add only 2 pairing energy and not 3 pairing energy. Okay. And now the crystal field stabilization energy is minus 2.4 delta O plus 2 pairing energy. It is a low spin D6 system. Low spin, why it is called low spin? All the electrons are being paired, instead it is not going to the upper side, or it is not going to the EG orbital. And now the case 2, D6 case 2, it is D6, 6 electrons, it will be splitted, and now while filling the electrons, 1, 2, 3, 4 will be going here, 5, 6, and this is a case where delta O is less than pairing energy. When delta O is less, the fourth electron will be obviously going upside or in the upper upper state or EG state, and the arrangement will be like this. While calculating the CFSE, how many electrons in T2G? 4. Stabilization energy of T2G, that is minus 0.4 delta O, and electrons in the EG 2 into 0.6 delta O. On total you have to add this and you get the value as minus 0.4 delta O or 4 dq. In terms of dq, you can write as 4 dq. This is a high spin D6 complex. And now D7 system. D7 system is also having 2 possibilities. Either you can pair in the T2G set, or you can go to the EG, and then after excess electron, after 5th electron, the 6th and 7th will be paired in the T2G. That is the case. And the first case is you are actually first pairing all the electrons first. That is the low spin complexes is considered here. This D7 means 7 electrons. While filling 1, 2, 3, we are pairing 3, 4th one is pairing, 5th one is paired, 6th one is paired, and now all the d orbitals in the T2G sets are paired. Now the extra electron, that is the 7th electron, is going to the EG orbital. This is the case, low spin complex. And now crystal field stabilization energy can be calculated, number of electrons 6 into minus 0.4 delta O plus how many electrons in the EG 1 into 0.6 delta O plus what is the pairing energy in this case? It is only one pairing energy. Why it is one pairing energy? That will be clear if we look the case 2. In the case 2, this is a high spin complex, the same system, D7 system, this is also D7 system. This is a case 2 where we are actually going to here the delta O is less than the pairing energy. Then 1, 2, 3, after the third, fourth will be going here, 4, 5, then it will be 4, 5, sixth will be coming here, seventh will be coming here. So, in this case, high spin complex case itself, there are 2 paired structures possible, and the extra one is paired here only in this case, in this case extra one is paired. That is why one pairing energy is already 2 of them are paired in this structure and the extra one is paired here. That is why one pairing energy. And the crystal field stabilization energy in the case 1 is minus 1.8 delta O plus 1 pairing energy. The complex is D7 low spin. And now the case 2, that is a high spin complex. I have already told that it is this is a case where delta O is less than pairing energy, that is crystal field splitting is less, which means that electrons will be going to the upper state, that is EG state, and then only the other excess electrons, that is 6th and 7th electron will be paired here. And while calculating, we can calculate the CFSE by numbering the electrons 5 into minus 0.4 plus 2 into plus 0.6 delta O, that is minus 0.8 delta O or 8 dq. It is a high spin D7 complex. And for D8 system, in the case of D8 system, we have only one possibility, no 2 cases are there. See, D8 system means D, how many D electrons? 8 D electrons. 8 D electrons are being given here, and after splitting you can add the electrons 1, 2, 3. If we are considering 2 cases, this is, suppose this is a case 1, which means that we are high spin, and if it is, now consider the case 2 low spin. Okay. If it is high spin, now consider high spin means delta O is, high spin means delta O is very much less, which means that how many electrons? D electrons. After the third electron, 1, 2, 3, after the third electron, fourth will go there, that is in the EG set, 4, 5, 6, 7 and 8. This is the arrangement. Okay. Now, the lows, in the case of low spin complex, you can write it as like this. Low spin means here delta O is very much less, very much greater, which means that it is very difficult for the third electron. After filling 1, 2, 3, after the third electron, fourth one will not be going to the EG set, it will be just paired here 1, 2, 3, 4, 5, 6. But you have the system D8, 6, 7 and 8. Now, after 6, it should go there, because after 6, 7 and 8 electrons, 7th and 8th electron should be filled. It should go to the EG level. See the difference. Is there any difference in the arrangement of the electronic arrangement in this both the cases? No difference is there. Both are same. That is why in D8 system only one case is there. Okay. And now while calculating the CFSE, you can add the number of electrons. 6 electrons in the T2G, 6 into minus 0.4 delta O plus 2 into plus 0.6 delta O, on the whole you have minus 1.2 delta O, or you can write it as 12 dq, minus 12 dq. And D9 system is also same. No, there is no two cases are there, case 1 and case 2 is absent in this case also, only this arrangement is possible, and we can actually calculate the CFSE by merely adding the number of electrons, and finally you got the answer minus 0.6 delta O, you can calculate. For the D10 system, you can see that D10 means 10 electrons in the d orbitals, all the d orbitals are paired. Now, by the approach of ligands, there will be splitting and the electrons can be filled like this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the only arrangement possible. And while calculating the CFSE, you can number the electrons in the T2G and EG, 6 electrons in T2G, 6 into minus 0.4 delta O, and how many electrons in EG? 4. 4 electrons into plus 0.6 delta O. On the whole, if we count, we will get 0 delta O. Crystal field stabilization energy is 0 in the case of D10 system. In the case of D5 high spin also, it was 0. And you can actually summarize this. This is the summarization, or this is the overall thing that we have calculated here. Here you can see the weak field and strong field ligands. Weak field means the ligands which are very weak, or the cases where the electrons are being, they are not paired, or the electrons are going to the EG level. That is, maximum electrons will be filled in the T2G and EG, and after that only pairing occurs. That is the weak field case. In the case of strong field means we are actually pairing electrons and then the excess electrons will be moving to the EG set. Okay. So, these are the up to I think it is up to D1, D2, D up to D3. We have only one situation, weak field and strong field will be same, and after D3 only the difference occurs. See this, if we take D1 system, D1 we have calculated, D1 means 1 electron, it will be in the T2G set, whether it is a weak field or strong field, it will be in the T2G set, T2G1, that is T2G1, see T2G1, T2G1, whether it is a weak field or strong field, 1 electron will be in the T2G set, and number of unpaired electron will be 1. Here also it will be 1, and while calculating the CFSE, it was minus 4 dQ. In the D2 also the situation is same, there is no change for the weak field and a strong field, because we are just simply filling the electrons. In the D3 also the situation is same, because there are 3 T2G orbitals, 1, 2, 3, they will be filled like this only. So, in the whether it is weak field or strong field, D1, D2, D3 will be the crystal field stabilization energy will be same. Now, the difference occurs from D4 to D7, from D4 to D7. D4, D5, D6, D7 will be having two cases, case 1 and case 2, that is a weak field case and a strong field case. When it is a weak field case, the maximum unpaired electrons will be there, that is unpaired electron, see the unpaired electron, it is 4, because T2G3, the after the third one, the fourth one will be going to the EG set. So, on the whole you have unpaired electron 4, the CFSE was minus 6 dQ. But in the case of a strong field ligand, see this D4 system means we are pairing, in the strong field means we are just pairing the electrons. So, first, second and third electron, after filling the third electron, fourth will be paired in the T2G set itself. That is why T2G is having 4 electron. So, in that case unpaired electron will be less, that is 2, and we have calculated the CFSE, that is minus 16 dQ, dQ plus 1 pairing energy. And now, D5 system, in the case of D5 system, there are also two cases arises, that is weak field and strong field. For the weak field case, we have maximum unpaired electrons, that is 5 unpaired electrons, all the electrons are unpaired, and you have the CFSE value 0 dQ. And but in the case of a strong field ligand, that will be the case will be different, because in this we are pairing the electrons, that is after third electron, fourth and fifth will be paired in the T2G set itself. That is why T2G is having 5 electron, and number of unpaired electron here is 1, and the CFSE calculated is minus 20 dQ plus 2 pairing energy. And the D6 case is also discussed, weak field and strong field, both are different, both are having different CFSE value, that is D6 for the weak field ligand it is minus 4 dQ, in the case of a strong field ligand, it is minus 24 dq plus 2 pairing energy. And now D7 is also having two cases, weak field and strong field, both are having different CFSE. And from D8 to D10, we have only one case, as in the case of D1, D2, D3. The weak field, whether it is weak field or strong field, the number of unpaired electron and CFSE is same. And this is the altogether calculation of crystal field stabilization energy in the case of complexes. And in this class, we have discussed about the modern theory, that is crystal field theory. The crystal field theory is all about the the removal of degeneracy of d orbitals by the approach of ligands, and several postulates were there for the crystal field theory. In the crystal field theory, the theory was emphasizing on the electrostatic attraction between the metal and ligands, and the removal of degeneracy by the approach of ligands, and the splitting of d orbitals into two, and the electrons filling according to the different types of ligands present, etc. And we have calculated the crystal field stabilization energy for various complexes also. And in coming classes, we will be discussing about next theories, more and more different theories will be discussed. And before that, in this class we have discussed only the crystal field splitting in this octahedral complexes. Further, in coming classes, we have to discuss the crystal field splitting in other ligands or other field also, that is tetrahedral field, square planar, etc. That will be discussed in the coming classes. And I thank you all for watching this video. Thank you.